Hello, and welcome to the Physics Help Room Online, where we go through the most common problems and concepts discussed in the Physics Help Room in detail to help you develop the problem-solving skills you need to solve these types of problems on your own in the future. In today's video, we will work through the ring of charge problem. The ring of charge problem goes something like this. You have a ring of radius A that has a total charge Q uniformly distributed around the ring. You are asked to find the electric field at point P, a distance x away from the center of the ring, along the x-axis. This may seem like a daunting problem. Where do we start? First, let's think of what equations we might be able to use to solve this problem. We have two ways of solving for the electric field in terms of charge. We could use Coulomb's law or Gauss's law. Due to the symmetry of the problem, we don't have a nice Gaussian surface to use Gauss's law, so we'll use Coulomb's law. Next, we ask if we have all the information that we need to solve this problem. At a glance, it may seem like we already have everything. We have the charge, and by using the Pythagorean theorem, we can solve for r. So we're done, right? Not quite. If the ring were just a point charge, we'd be done. However, the ring is a two-dimensional object, meaning that we're going to need to use vector addition to solve this problem. Let's see if we can come up with a more appropriate example. Let's determine the electric field generated by 2 point sources, which are located a distance x away from point P along the x-axis and a distance a away from point P along the y-axis. In order to solve two-dimensional vector problems, we must split the vector up into components and solve for these components individually. Let's start by determining the y component of the electric field. From the bottom point charge, the component we obtain is kq over r squared sine theta in the positive y direction. The y component of the electric field generated by the top point charge is equal in magnitude, but opposite in direction. Therefore, the total y component of the electric field generated by the point charges experienced at point P is 0. What about the x component of the electric field? The component from the bottom point charge is equal to kq over r squared cosine theta in the positive x direction. The component from the top point charge is the same, meaning that we can determine the final electric field by adding them together. However, we are now left with two variables that were not given to us in the initial problem, r and theta. We already determined that we can solve for r by simply using the Pythagorean theorem. Now that we have r, we can solve for the cosine of theta using simple trig rules. We can now obtain the x component of the electric field by just plugging these values in. We now have the solution for our electric field. But how does this problem relate to our initial problem? Well, instead of just 2 point charges, what if we had many point charges that were evenly distributed to form a ring? As we saw from the previous example, the y and z components of the electric field would be equal to 0 because the symmetry of the system would cause them all to cancel each other out. We are left with an x component of the electric field that is equal to the sum of all the individual x components of the electric fields generated by the individual point charges. You can look at the integral that we will use to determine the electric field as just an infinite sum of all the x components of the electric fields generated by infinitesimally small quantities of charge that we will call dq. But if we have an integral that is dependent on dq, how do we define the boundaries of integration? We need to rewrite the integral in terms of spatial variables that we can integrate over. In order to do that, we ask ourselves over what dimension can we integrate dq to obtain a total charge q for the ring? The answer is phi. If we sum up all the dq's by going around the ring, in other words, by going around the angle phi, we should obtain the total charge q in the end. But how do we write d phi in terms of dq? For this, we come up with a charge density that is dependent on phi. Because the charge is evenly distributed around the ring, We know that the ratio of charge to angle must be uniform throughout. Therefore, we can say that the ratio of the infinitesimal charge to the infinitesimal angle is equal to the ratio of the total charge to the total angle. We can check to see that our charge density is correct by integrating it over the ring, and indeed, we obtain a total charge Q in the end. Now that we have the charge density, we can write dq in terms of d phi. Since phi is not dependent on any other variable, and since all the other variables are constant, all the variables except for d phi can be taken out of the integral. When we integrate d phi from 0 to 2 pi, we simply get 2 pi. The 2 pi's in the numerator and denominator cancel each other out, and we are left with our solution. And that is how you solve the classic ring of charge problem. Thank you for visiting the Physics Help Room online. If you have any comments or suggestions, please post them below.